Hello everyone, this is video 11 in my series of trying to solve Project Euler problems using the NIM programming language and using Google's Gemini 2.5 Flash to learn along the way. So, um, problem 11, let's go through our routine. Getting a screenshot and going to Excalibur. Alright, so what is the problem saying? In the 20 by 20 grid below, four numbers along a diagonal line have been marked in red. Are 26, 63, 78, and 14 diagonal. Okay, the product of these numbers is 26, 63, 78, and 14. Is equals to 1788696. What is the greatest product of four adjacent numbers in the same direction, up, down, left, right, or diagonally in the 20 by 20 grid? All right, so simple enough. This is a 20 by 20 grid, and for each number we take four adjacent numbers in. Ooh, that's too big. Oh, still too big. Oh, it's too big. Okay. Maybe. Oh, that's room two. Cool. Maybe I should have done that early on. All right. So, in this 20 by 20 grid, for each number, for example, 8, we take four numbers in the right direction. So that would be 8, 2, 22, and 97. Four numbers in the down direction for this 8. So that would be 8, 0, 0, 65, and 91. We take numbers in the left direction, and for something like this 48, we would take numbers in the up direction, and something like this here in the diagonal direction. Okay, so simple enough. And we want to take all possible four subsets out of this 20 by 20 matrix and uh, find the product of four adjacent numbers that is the largest. So I think to map out the logic of this, at first we need to actually have this matrix in our programming environment, somehow implement this as a matrix, and once we've done that, find a way to iterate or go through all these numbers and find all the adjacent numbers. So this would be implement matrix. And then after we implement matrix, we can take a implement iteration to go through each number. So we would go through 0, 0, and then after that we would go through, this looks like a face, an owl's face for some reason, but all right. Then we'd go through 1, 1, 0, 1, and then we go through 0, 2, and then for each of these numbers we find a right, and then find a left, then find a up array, and then we find a down array, and then we find diagonal arrays, and then afterwards we get a product of each subarray. Product of each subarray, make note of the product, make note of the current product, and check if current is larger than the last biggest product. Let's call this placeholder final product for now. And then if it is, then we will probably swap these. And then at the end of it all, once we have gone through all the numbers and all the subarrays possible for adjacents possible for each number, we will just echo the final. So that's the business logic. Not at all too difficult. Not at all too difficult. But then what will the implementation logic look like? Right, so implementation logic. All right, so I think the first step of the implementation logic would be to somehow take this matrix that we can visually see for our own eyes and implement this in a programmatic way. So my solution for this was to just copy the whole thing. Here, we can now go to our programming environment and do hx problem 11.nim. We have done enough nim at this point to know that we need import sequtils. The library that we will need to work with seqs. So we import sequtils, and my solution to this was just copy the whole thing and paste it as a flat array. So something I'm doing is making snippets, making meaningful snippets that I'm keeping here on the right and copy pasting those snippets into my editor to spend less time actually doing the typing and try and spend more time doing the actual logic. I hope that's okay. It seems reasonable to me to spend less time actually doing the typing and spend more time explaining the logic. So I copied the whole thing over and pasted it as a flat array. Now, once I had a flat array, right, this is our flat array, I know that every 20 elements of an array is a row or a column, however you want to think of it. These are the same lengths. I'm just doing, these are the same lengths. These are 20 and 20 and 20 and 20. These are the same lengths. They just look different lengths because I'm eyeballing and working with my hand. So I'm doing the freehand. So each 20 of these belongs in a row of a matrix, right? So this here is the matrix, and then this one belongs. This one belongs here, and this one belongs in the second one. So this is 1, this is 2, and this is 3. It's a very wonky 3, and then we will have a 4 over here. So every 20th element of a flat array is the row of a matrix, or the column of a matrix, however you want to think about it. And a matrix is really just a sequence of sequences, right? A matrix is just a sequence of sequences. You can think of it this way. This is the actual representation. This can be the actual representation. And the human eye will see something like this. But you can always think of it as just a sequence of sequences. So our question to Gemini now then becomes, in the NIM programming language, how do I make a seq of sequences of type int? I have a hunch for what the answer for this might be, but let's see what Gemini says. Seq of type int. So that is what I did. So we will now make a sequence of sequences using the syntax we got, and then we will go through our flat array, and for every 20 of them, we will make a sequence inside of a sequence, of a larger sequence, right? So a secondary sequence, one of the secondary sequences inside the primary sequence. So that is implemented like this. So the name of this is flat array, and for I in flat array, add it to the row, keep the count, and once the count reaches 20, increase count and go to a new array, which also means we need the preamble. We need the preamble for this logic, which can be implemented like this. So in nim, turns out what you can do is just have var and then indent one step and then make a bunch of objects of the same type var in one block. To me, this is a fantastic way to block your code and make it more easy to read so that I'm not typing. It also saves me a lot of time. I don't have to do var in front of every line. I don't have to do var in front of every line, and then it also helps me represent my code like parts of an essay, right? Almost better. So here, array2d is a sequence of sequences. Initialize it, and then a row is a placeholder that will become one of the secondary rows in our sequence of sequences. Count to 10 is an int, and row count is the index of the item for the current row, right? So you will need an index for this. This is 0, but then this will have an index of its own here, right? And this will have an index of its own. So that's what row count will represent, and that's what count to 10 will represent. So my LSP is telling me there's an issue, but for now, I just want to see if everything looks right so far. So I can't tell what the issue is according to my LSP. Oh, there we go. Okay. And now what we can do is just this, right? Here's a proc that I defined to see if what we're doing is right. If we have converted a flat array into a matrix. So proc print matrix, you send it a created matrix, and for every element we will try, for every row we will print a row, and then we'll print the elements in the row. So let's see if what we have done so far looks right. All right, so that looks like a matrix to me. So 849, 81, 52, 849, 81, 52, 89, 19, 67, 48, 89, 19, 67, 48. Yeah, that looks right. If anything goes wrong, we can always come back to it, but for now, we are to a point where we have made a matrix. So I'm just going to comment that out and move on to the next part of the problem. All right, so now that we have a matrix in our programmatic environment, let's see how we can go through this matrix. So this matrix has two dimensions. Make that blue, and oh, well, sure. This vertical direction and this horizontal direction. Now let's call this I, and let's call this J, right? So for this number 8 in the first row, the I is going to be 0 and the j is going to be 0 as well. For 2, I is going to be 0, j is going to be 1. So that's just a good old simple double nested for loop. You go through I, and then you go through j, and then you can keep going through all your numbers, and then finally you can go to once you start with 0, 0, and in this case you will end up with 20, 20, right? All right, so we have a matrix and we know how to access values inside the matrix. Or syntactically we don't know that yet, but we know the underlying concept. So how can we now get the multiple different kinds of subsets we're supposed to get? So for example, for a right subset, we would go here, right? We'd take these 4. But then we don't want to try and get a subset past this 50 because that will lead to a crash. That can lead to a crash unless we account for the logic to make sure that our program doesn't crash. For a left subset, we can't get a left subset before 97 here because there's only 3 numbers here. For an up subset, we can only do it here. We can't do it here or here or here. Similar thing for a down subset and similar thing for diagonals, where we can do 8, 49, 31, and 23, but we can't do 49, 31, and 23 or something like that. And we can expand that concept to the whole 20 by 20 grid. So we need to make sure we stay within the right bounds. We stay within our boundaries. And then we also want to make sure we record all of the subsets, take their multiples, and then after we're done recording that, we compare it to the last biggest one. So once you're within boundaries, make sure you get these subsets, get their product, compare, and then finally print. So I think to me that looks like this. Implementation-wise, that looks like this. An outer loop that goes through the rows, an inner loop that goes through columns. And then for every number now we want to, for the right subset, we want to, the I is 0, and the I is 0 for this 2, and the I is 0 for this 22, and the I is 0 for this 97, but the J is 0 for this 8, the J is 1 for this 2, the J is 2 for this 22, and the J is 3 for this 97. For a left subset, the I is 0, 0, 0, and 0, but the J is 19 index-wise, and the J is 18, and the J is 17, and the J is 16. For the diagonal, for something like this diagonal, the I is 0. For the 60, the I is 1. For the 71, the I is 2. And for the 68, the I is 3. So the I is increasing. Now, just to make sure I do make it clear, I want to use a different number here. Now the J is, let's say 11, and the J for this, the J is 11 for this 40, and then 12, and then 13, and then 14, right? So for diagonals, both for the right diagonal, both I and J increase. Both I and J are increasing. For the right, to go in the right direction, the I stays the same, but the J is increasing. To go in the left direction, the I is decreasing, but the J stays constant. Let's see what that looks like for the left diagonal. For the left diagonal, if we're going to do an 8 and a 62 and a 13 and a 71, so the I is 0. Sorry, the I is not, so the I is 0, and then the I is 1, and then the I is 2, and then the I is 3, and the J is 19. Oh, let me do that a different color. The J is 19, and then the J is 18, and the J is 17, and then the J is 16. All right, so go through I, a for loop that goes through I, and a for loop that goes through J, and then some more logic to get relevant subsets with their respective dynamic of I and J. So this is where the implementation details got interesting for me, and let me show you what I mean by that. So now that we're here, we know that we want to go through each number. Primarily, we want to go through each number, go through all of them. And secondarily, we want to make sure we stay within bounds. So one of the ways you can do that is say this is index 0 and 1 and 2, and this is 19 and 18 and 17, and same thing in the up and down direction. So one thing you can do is, for example, for the right direction, you kind of say, hey, don't go past, only go up to 16. Only go up to 16. For the left direction, you can do only, oh, hey, only start with 3. Don't. For the up direction, you can kind of do, hey, if you're less than something, for example, 0, 1, 2, and 3, oh, hey, only start with 3. And for down, you can do only ever start with, don't go past 0, 1, and 2, and 3, and then do the math in your head, and then only don't go past 4 minus 3 here is 1, in that it would be probably 17, right? But this is error prone. I think what we can do is go through each number, go through all of them, apply our diagonal logic and right logic and left logic, and then if we can get 4 proper numbers, get the subset, and then if we can't get the proper numbers, we tell the program to stop, take a step back, and then go to the next number. So in most programming languages, that's called a try-catch. And Nim has this too. So in the Nim programming language, please show me the syntax to do a try-catch. Right? So try, except, some exceptions, except finally. Cool. So the error we want to avoid is, for example, if we are out of bounds, right? So what does Nim call the exception or the error where the program tries to access a sequence beyond its bounds? Index defect. All right, so what I suggest we do then is we are in our I iteration for rows, J iteration for columns, and then we do, I'm sorry about the browser one more time, I'll try to find out why that's happening. But for the right arrow, we try for each number to get three more numbers to its right, or four numbers for that number, and then we catch any index defects. Any index defects. And move on, right? So in that way, we don't have to do all this math in our head. We could end up with a 20 by 20 grid, we could end up with a 40 by 40 grid, or a 100 by 100 grid, or any other number, and then we could just change a small thing and keep going. So this saves us this mental arithmetic and makes us much more robust and much less error prone. So I think that's the better way to go about it, right? So I was implementing that. I was trying to implement that. And in the process of trying to implement this logic of go through I, go through J, and try right logic and left logic and up logic and down logic and all other kinds of four subsets per number, I discovered something interesting that I think is worth showing. So I want to show that with a different snippet. So basically my idea was we have an array or an array-like structure that looks like this. So 1, 2, 3, 4. And we go through an index for I from 0 to 3. And we will try for k in a second index to print values of k or access values of k. So as you can see here, there are only 4 values in this sample sequence. But for k, we're trying to access the fifth sequence that doesn't really exist. So this echo will try to access the fifth sequence that doesn't exist, which should cause an index defect, and I want to continue from here. Turns out that's a mistake, right? So let me show you why that's a mistake. So I was hoping what the logic would do is go through i's, and for every I, go through a k. 5 doesn't exist, but 0 does exist. 0 is 1, and then print the value of this zeroth item of sample sequence, tell you the value of I, and then finish this for loop, and then move on to the second try catch where we can we can go through more of our logic downstream. So here I would do a try catch for the right block, and then I would do a try catch for a second block. That was my idea, and then I for the left block, and then the up and the down and the diagonals, right? So that was what I was hoping to do. Now let's compile. I call that file issues with continue, or my misunderstanding with continue, right? So if you do that, it's not going to print anything, right? So what is happening here is we have a 4-item sequence. We want to try and print the fifth one. We know it's not there, but just for practice sake, we want to try and print the fifth one. And then if the fifth one doesn't print, we want to try and continue in this for loop with k, try and continue to 0. But turns out that's not how it works, right? Because the continue is being applied to the I and the for loop that has the I and not the k in it, right? So that was something that bugged me for a long time. I did not realize this. I could not tell where the issue was coming from. But in hindsight, it looks very simple. But turns out, if you're in for loop A and then for loop B, and then you apply a try and a catch, and then you do a continue, you have a for loop here. I know this is at this point a triple nested for loop, and this is horrible, but I'm trying to do first principles and just trying to learn and hopefully implement better solutions in the future. But if you do continue, this continue will be applied to B. That makes sense because there's no connection between this for and this continue. So then I had to ask Gemini if when working in the NIM programming language, if I have a for loop, let's call it loop A, and then a try-catch block where the try block has a second for loop B, loop, let's call it B, and if the catch block has a continue, will the continue be applied to loop A or loop B? Loop A, right? So it will be applied to the outer loop. So if I want a second try catch, which means it will be applied to this continue, this second try block or subsequent try blocks will never be applied, and it will move on to the second I, and then we can end up in a situation where we choke here and then never apply. We choke in the left logic here. We choke in the left logic here in the try catch, and then every other try catch does not get applied, right? So it turns out I kind of ran into this issue, and it was just a lot of debugging and a lot of tinkering and a lot of playing around with variables and a lot of print debugging because the program wasn't crashing. It was doing exactly what I told it to, but not giving me the right answer. So it was a lot of print-based debugging that led me to discover this. But in retrospect, it looks obvious, but in the moment, it did not. So now then my question becomes, is there a way I can break out of an index defect, but still have subsequent logic be executed? So if I want a second try catch block inside loop A to be executed, continue is not the right logic. That makes sense. What options do I have if I want the first try catch block to catch its exceptions, but want following logic, but next blocks of logic such as a second try catch to still be executed? So this is saying if it's some exception this, you can continue onto some other exception that. But that's not the solution I actually stumbled into. I don't quite know how to present this, but the solution I ended up on was no, the the exceptions for both the blocks try catch blocks are the same. So I think what I want is that iteration of loop A that causes the exception to fail in the first try catch to be skipped, but still move to the next try catch, which implements different logic that can still cause the same exact exception. Okay, so it's saying if you, so long as you don't put a continue here, the next I, for this iteration of I, the second try catch block will still be executed. What if, and it's telling us we can use echo as just a way to not continue but do something with the except index defect. What if I don't want to bother the end user with a bunch of echo statements to std out? I want to just move to the next try catch block. Now, I will say that Gemini did not quite do exactly what I wanted to do with that question, but it did give me a lot of useful information that I did have to look at and read. So it's still important to pay attention to what you asked, what it answered, if it answered what you asked, or gave you a right answer, but for a different question. It can happen. You ask question A, it thinks you have asked question A.1, and then it gives you an answer for A.1 that is very similar and related to the question you have asked, but not exactly what you needed, right? So it's saying echo. Right. So I don't want to do echo. I want to discard. So that's what I should do, right? So that's the answer I was looking for. I'm sorry I had to do this in a very convoluted way. But so if we do, for now, what's happening is in this try catch, I mistakenly caught the index defect, but I did continue, which then moves on to the second I. So we are at 0. We try to we have an index defect, and then because there's a continue, the I will move on to 1 without going to the second try catch block, which is not what we want because we want to implement multiple try catches for rights and lefts and ups and downs and left diagonals and right diagonals. So what I can do is replace continue with discard. Now, even though this try-catch block now fails, what we should now see is that the second try-catch block will be executed, which was not the case in the previous iteration. And as you can see, it does go to the second try-catch block now. So with that in mind, now all that's left to do is implement the for loop. that goes through I of array, and then it goes through j of array, of j of the current row of I, and dot len is how you get the length. And then go for a diagonal, we will do try catch for k and 0 up to 3. We will do 0 up to 3, we will do because to move diagonally meant we need to increase I, increase j, and increase I, and increase j. We will at first we will take the number and add 0, just the number. That's how you get the number. And then we will add 1, and then 2, and 3. And then we will use fold L from the seek utils to get the multiple. If the current multiple is greater than the final multiple, we will replace the final multiple with the current multiple. And then we will replace the final seek with the current seek. If there is an index defect, one thing you have to do is empty the current sequence, and then move on to the second try-catch block that we will implement here in a minute. And so one thing to take a step back, once we compare the current multiple with the final multiple, or the last biggest multiple, we also want to make sure that the current sequence has been emptied. And the way to do that is current sequence dot set len to 0, right? So now we also need a second set of variables here, which will be var current seek int final seek int shift add current multiple, which is an int, set it to 0, final multiple, which is also an int, set it to 0, right? So now that we have done diagonal, what we want to do is implement the left diagonal. Implement the right diagonal. Implement the right subset. Implement the up subset. Implement the down subset. And then finally echo final sequence. And then echo final multiple. Fingers crossed. The final sequence of the 4 numbers that produces the biggest product is hopefully 89, 94, 97, and 87. And the multiple is 706000674. And let's see. That is our answer. We will go to Project Euler. We'll go to Project Euler, sign in. Copy the right answer. And see that it is 706000674. That is one more Project Euler problem done. Oh. So this was one more smiley face. I am happy that I implemented sequence of sequences, seeks of seeks. I learned about using var for multiple variables I learned the difference between continue and discard. Continue versus discard. I think that will be useful for me in the future. And continue and discard, I learned how to, oh, one thing I forgot to show is if you have a matrix-like structure, the syntax to access that is array. So to access something like the first row, the first item, oh, the first row and the first column would be 0, commas 0 and 0. So it will be array name, square brackets, and square brackets. So that's the way to do it. All right, so that's how you would do it. I learned how to make a matrix out of this seek of seeks. I learned how to access it, and I'm fairly happy about having learned the difference between continue and discard. That it looks very obvious in hindsight, but in the moment it kept tripping me up. And I'm very happy about this NIM's way of representing multiple variables at once. It makes uh, it gives me a way to eloquently represent code. So I'll see you guys in um, problem 12. Looks a bit gnarly. We will read it. I'll read it and then try to work on this. All right. Thank you. See ya.